Hi, everyone. Welcome back to For Climate next session. We're just going to wait here for a few minutes, but we are ready with our next speaker here, and we shall be back in a few minutes. Let's wait while we wait for others to trickle in. All right, so I think let's get started. So up next, we have a case study discussion by I-Kang Ding. The discussion would be about data mining techniques. We would be applying ML and distributed computing on, or how he has, applied ML and distributed computing on large-scale geospatial data to discover the battery metals critical for solving climate change. But before we get started, I would like to introduce I-Kang. He's a data scientist and machine learning engineer with over a decade of experience in several fields, including mineral exploration, financial services, semiconductor manufacturing, and solar cell R&D. He has years of hands-on experience with the full life cycle of machine learning models at scale, from business problem definition and refinement to data and feature pipelines, model development and model deployment in production. He's also worked as a data science manager at Capital One prior to these roles, where he was applying machine learning models for credit card fraud detection and projects of that nature. With that introduction in place, I think over to you, I-Kang. You can go ahead and share your screen, and the stage is yours.
Wanting to make sure people can see my screen right now.
Yes.
Okay, great. I'll go ahead and get started. Thanks to everyone. My name is I-Kang. I'm a staff data scientist at Cobalt Metals. We're a startup working on using AI and ML to find battery metals to solve climate change. So today I'm going to talk to you about some of our recent work on using ML on large-scale geospatial data to do that. So before I begin the talk, I'm going to start the talk with some macro trends and set the stage for the big challenges that we're dealing with. So as many of you know, electric vehicles are key technologies to decarbonize road transport, and that's a sector that accounts for around 1/6 of global emissions. And the good news is that the EV sales has been rising significantly in the past few years, from 4% in 2020 of all the EVs total sales to 14% in 2022. What you may not know is that EV also uses significantly more minerals than internal combustion engine vehicles do. On average, EV uses 6 times more minerals than conventional vehicles. So in 2023, an average EV contains around 140 kilograms and $4,300 worth of this for minerals. Copper, which is used in wirings and electric motors, and lithium, nickel, and cobalt, which are used in lithium-ion batteries. So the next slide, I'm going to examine the supply and demand for these 4 elements in more detail. And this is showing the supply and demand for these metals for the next 30 years. For each of the 4 elements, copper, nickel, lithium, and cobalt, the horizontal axis is the time from 2020 to 2050, and the vertical axis is the annual production. So down in the bottom, you have the gray wedge, which is the current mine supply. And that contains projects that are currently producing, as well as projects that are very close to being online, and that's the gray wedge. And the next wedge in lighter color is the recycling. For recycling supply, we make the most aggressive assumption that we can, which is that 100% recycling in perpetuity, which is physically possible, but the reality is that the recycling rate is likely going to be a lot lower. And at the top line, you have the projected demand in order to achieve the electrification of light-duty fleet globally by 2050, which is about 2.5 billion cars on the road globally in 2050. And if you take the demand on the top and subtract away the known supply, what you're left is the wedge in the darker color, which is the supply of new metals that is needed to bridge the supply gap. So for something like lithium, where the supply gap in the next 30 years is accounting for $6 trillion, that growth in production is staggering because we're looking at something like 30x increase in the production between 2020 and 2050. But it is also true that for lithium, at least, we start from a very low base because we had almost no exploration efforts. Lithium mostly became an essential and highly valued commodity in the past 10 to 15 years, thanks to the rise of lithium-ion batteries. On the other hand, you have copper, which is only doubling from the baseline, but the baseline is gigantic because we humans have been exploring and mining copper for thousands of years. And nickel is a bit of a medium case between copper and lithium, and cobalt is a bit more like lithium than like copper. So combine these four elements, basis supply shortage that is worth around $12 trillion with today's commodity prices. This is a serious challenge. If you look at the median mine outputs in the industry, that supply gap is roughly equivalent to 1,000 new mines that has to be found and developed. So at the same time, the industry has been spending more to get less. This graph is what we're calling the Eroom's law, which is Moore's law spelled backwards. It's a wordplay because in mineral exploration, we have been spending more. So the dollar of exploration expenditure for tier 1 and tier 2 discoveries has been down by around 8x in the past 30 years. And why is that? Well, one of the potential reasons is all the easy stuff has already been found. So the graph that we're showing here is the mineral discovery in depth and time for the three ore type that we're actively searching for: the nickel, copper, cobalt, magmatic sulfide, lithium pegmatites, and copper, cobalt, 7 hosted minerals. And on this graph, the horizontal axis is the year of discovery, and the vertical axis is the depth of the centroid of the deposit. You can see that for the past 100 years or so, all the discoveries are virtually all at the surface and directly detectable at the surface. What that means is that if you are a skilled geologist, you can walk up there, you can see you can see the ore minerals in the outcrops, or you can measure anomalous concentration of minerals in either rock, soil, or regolith sample. And even those ore bodies that are found in depth are often follow-on discoveries. So what people may have is they found shallow ore body first, and as they dig deeper, they found ore bodies that are related to the first one during the mining of the process. And you might look at this and ask the question, well, maybe these ore bodies just form at the surface. Maybe that's why they're all there. But we know certainly for the ore system that we're looking for that it is not the case. These ore systems are typically formed deep underneath Earth's crust, and they're only exposed to the surface through post-formation tectonics and erosional processes so that they're exposed at all. And that is actually good news because we know there's a lot more ore bodies in the depth waiting to be found, but finding them gets a lot harder. So combined with the supply gap and the decrease in exploitative effectiveness, we have a big challenge ahead of us. So for cobalt, our objective is to invent new techniques and technology to improve the efficiency of exploration in every single step of the process. You can think of the steps as a funnel from very large length scale from the left and decreasing uncertainty and decreasing length scale as you move from the mining districts to prospect to individual targets, eventually discoveries and resources. So our talk today will be focused on the earlier stage of this funnel, which is focusing on the larger length scale in the district and prospect level. So now let's start with the original prospecting with length scale around 10 to 100 kilometers. So to start, I'm going to give you a very quick primer on the particular ore system, which is the magmatic nickel sulfide ore system. This is where the high purity class 1 nickel comes from, the type of nickel that is predominantly used in lithium ion cathodes. So in this ore system, how these ore bodies form is that the magma comes through in some conduit of the earth, and this magma are mafic and ultramafic magma in nature, high in magnesium and high in transition metals. And in Earth's crust, they can interact with some sources of sulfur, usually in sedimentary rocks. And sulfur, when they're dissolved in magma, is very good at forming immiscible melts and scavenging these transition metals out of the magma and enrich the concentration of these metals, sometimes by a factor of 1,000 or 100 or 1,000. And eventually the magma can go out and show at the surface. And here's what a magmatic sulfide ore body might look like spatially. So the ore bodies are typically hosted in the mafic and ultramafic intrusions. Ore bodies that are shown in the red and schematic are often in the keel, like the keel of the sailboat of this intrusive units. And the ultramafic intrusions that's shown in the green schematic can be exposed at the surface. So for magmatic nickel exploration, there's a huge benefit in just knowing where the green rock or this mafic and ultramafic intrusions are. So that's the ore forming process. And now let's look at an example of our exploration work. So in this particular setting, we're going to discuss a project that Cobalt has in Cape Smith Belt in northern Quebec. This is what it looks like out there. You can see that it's very rugged terrain. It is very remote, close to the Arctic Circle at 61-degree latitude. And everything you need in this area, you have to fly in, and you have to have a helicopter-supported field program because the field is very big and the terrain is very rugged. So there's no way you can drive cars on here. In this area, our company has a claim of around 1,400 square kilometers of area, which is about 12x the size of city of San Francisco or 23x the area of Manhattan. And this area is covered by snow 9 months a year. So with all these rocks, we have truly a value of information problem. You only have 3 months of every year that you can collect data, and you have so many rocks. And where do you send a geologist to collect rocks? Because we cannot possibly sample them all. Our first field season here, our team took around 5,000 kilograms, which is like 5 metric tons of rock samples. Getting that much rock out of this remote area is a logistical feat, but it's also true that that 5-ton worth of rock is minuscule of all the materials out there. So we have to make sure that we are collecting the right type of rock. So our solution to that problem is to build an ML model that allows us to predict the surface lithology with high precision. So even before we set foot in the field. So the way that we build our ML model is to use both remote sensing and geophysical rasters as inputs and perform processing and transformation on the data and train ML models with geospatial inputs to predict the outcrop lithology. So outcrop is a fancy name of saying exposed bedrock, and lithology is a fancy name of saying type of rock. So we're trying to predict the type of rock that are exposed to the surface. So this kind of ML model can take place on a regional scale of 10 to 100 kilometers. And later in the slide, I'm going to show you some snippets of our approach, applying that to a continental scale of over 1,000 kilometers. So obviously, this slide did a lot of simplifications because the input data that we have on the geoscience is oftentimes end-member messy because they come from a variety of historical sources, some human inputs. They can come in a variety of historical formats that are like proprietary in nature, and there's a whole bunch of missing data and georeferencing issues, etc. So we, as a team, spend a lot of time dealing and proactively catching these issues in our data pipeline. And the tooling that we use to allow us to process geospatial data is primarily using dask clusters. So what we can do is that for the raster, we can farm out computations by chunking and tiling data sets and compute results and rejoin them later. The nice thing about dask is that because it's Python native, it allows us to use code locally and develop code in our laptops and with all the scientific computing libraries that Python has to offer. And after we got it to work, we can scale the computation to clusters with minimum change in the code. So our training label in this case are the known outcrops, which is exposed bare rocks. In a very small set of area, we have our geologists manually label polygons of known outcrops and outcrop type. So this comes with very good geological descriptions, and we have a high degree of confidence of the rock type and their boundaries of this polygons. And this is what the training data look like. I should note that curating and training data like this is really, really hard because it requires a lot of domain experts' knowledge and time and dealing with messy data in the label. And it's not something you can easily outsource to contractors or mechanical turks, for example. The ML portion of this problem is relatively easier in comparison. So for our training data and training labels and combined with our ML pipeline, what we're able to make is the lithological or type of rock predictions with meter scale resolution over an area of over 1,000 square kilometers. And we can use these maps to guide our field programs about where to prospect. What you're seeing here is what's called a composite of 6 different rock types or lithologies over one of our claim blocks. And maps like this allow us to inspect the regional distribution and variation of the geology and the lithology over a very large area in a short amount of time. And what we can do is we can look at the map and send our geologists to the most prospective areas. But another way we can use the models to use in-field observations to minimize uncertainty and improve our models further. So if you recall from earlier slides, we want to optimize the information we can gather from our very short field season. We want to collect the right type of information in the right location. So what you're seeing here is an initial model, a 3-class model that before we set for the project. So these models not only give us information about the probability of lithologies, they also allow us to quantify the uncertainty. So the next panel in the bottom left is the uncertainty for the day 1 model. So this is the per pixel uncertainty for the 3-class model. Each pixel has 3 probabilities associated with it, 1 for each class. So if one pixel has, say, 1/3 of lithology A and 1/3 of lithology B and 1/3 class C, then the model is not very confident about the prediction. This has a very high uncertainty. On the other hand, if the model says, hey, this pixel has 98% class A and 1% of class B and class C each, in that case, the model is very confident about the prediction. But if the model is very confident, then that is a low value information point. But if I can make an observation on locations with high uncertainty, we can dramatically increase the model performance with few observations. So that is what we did. In fact, we set up several field stations, primarily guided by the uncertainty at 4 different locations on this crop. And we take the measurements on these locations. And after those field observations, we can rerun the model. And you can see the prediction looks quite different. It looks a lot sharper, and the boundaries between the lithological units looks a lot more coherently defined because the model becomes more confident in being able to identify what type of material there is on the surface. And when you have quantified uncertainty, you can also see the model is way more confident. And we can do this by just collecting a handful of high leverage, high uncertainty field observations. So I want to show you what the model performance look like, but before I go there, I would want to take a brief detour to describe our cross-validation methodology, because that might not be obvious to those who are not working with geospatial data. So cross-validation is a technique that is used in many model assessment tasks and selection tasks. A common way to do cross-validation is called K-fold, where you randomly split the data into K smaller chunks, and you can train a model using K-1 smaller set and take the assess or evaluation or validations on the left out testing set. So that approach works well if your data set satisfy the IID assumptions. If you apply this on the geospatial data, that approach is an issue. So here you're seeing a schematic of a random k-fold on the geospatial data. These are points in space where the x is the eastern coordinates and the y is the northern coordinates. And what the problem that we're dealing with can be boiled down to a very simple statement, which is attributed to the first law of geography. Everything is related to everything else, but near things are more related than distant things. Well, duh, but this simple idea has a huge implication in cross-validation. So in particular, if you look at a cross-validation scheme above, a truly random split would oftentimes result in neighboring points being assigned to both train and test groups, which would make the model be able to cheat and give inaccurate representations of the quality of the model outputs. Because if you know the point, the truth point in one place and your test point is right next to it, chances are pretty good that these 2 points are highly correlated. So how do we solve this problem? The approach that we use is to use blocking, which is that when we resample our data to get our validation sets, we can resample them randomly to get blocks of the data instead of randomly sample individual observations. What this allows us to do is to guarantee that no training observations will be spatially interdispersed with our validation data set. So in our model, we use a 5-fold spatial cross-validation. And what you can see here is that the training points are split into 5 groups based on the squares on the spatial grids. And we end up training 5 different models, and each model is trained with 4 of the CV groups and evaluated using the 5th. And with this, we can obtain a better measure of the model quality. And that's something you see on the right on the precision recall curve. So 5 models, and the black line is the mean performance of all 5 models. And the horizontal axis on this is the recall, which is the fraction of true positives that is correctly identified. And the precision is the y-axis is the samples that we predict is a positive, but the fraction of it was actually positive. So the reason we have a precision recall curve is that because the model gives you a probability, you have to determine the probability threshold in which you want to split the prediction into positive or negative. This provides you with some flexibility to tweak the trade-off between predictive power of precision and recall. So if you set your threshold very, very low, so you have to satisfy a very low probability threshold to be called positive, what you can do is to have a very high recall, catching all the true positive, but you'll end up with a horrible precision and very high false positive rate. And you will be ending up in the right-hand side of this curve. And you can do the opposite, where you use a very stringent threshold, and you would get a low recall and high precision. So these models, being very close to a perfect square, to the top, to the right, up and to the right, is really, really good. We were very, very surprised as to how the models perform. So that means we have a precision recall of both over 90%. So how we use this model in Cobalt is also quite different from others, because we use the models in our own solutions to further our own exploration program. Cobalt, we are in the business of making mineral discoveries. We're not in the business of selling modeling tool or selling our services as a consulting boutique consulting shop. So after we have the model, we put our money where our mouth is, and we send our team to the field to do prospecting for this area. The model allowed us to discover several mineral occurrences that are previously unmapped, and that in turn led to a series of drilling campaigns and other activities that brings the Cape Smith project from the earlier stage to a more advanced stage exploration program. So what you're seeing here is an example of a mineralized boulder that we have found, which you can see there are native copper in the rock. So the rock is so choke full of copper that they precipitate out and form copper that you can see from the fraction. And I want to mention that we also can scale the same approach to the continental scale of over 1,000 kilometers or larger. So in here, we have expanded the methodology to Western Australia, and now covering an area that's over 700,000 square kilometers, which is slightly bigger than the California and Oregon state combined. And we can apply the machine learning models to this area and allow us to predict both the outcrops and the efficiency of the outcrops with this large scale. And dealing with a geospatial data within this scale is hugely taxing for the computational resources. But because we have the pipeline set up to deal with this geospatial data in the first place, our data allows our data tooling allows us to run the model end-to-end in under 15 minutes over a very large area. So that is where I want to leave the talk. And I should note that Cobalt, we have active hiring for data scientists of all levels, and we're also looking for a senior decision scientist to help design our intelligent system to guide mineral exploration decisions. The tech stack that we use is Python-centric and AWS-centric. On the geospatial computing side, we use a lot of DAST and X-array in our data stack. So with that, I would like to conclude my talk and see if there's any questions. So I see a question about battery production evolving. So let me repeat the question. Do you see a battery production evolving so we don't be so reliant on rare minerals? What is preventing this from happening? That's a good question. And I think this is a topic that is worth its own talk, and it's not the focus of my today's talk, and also not my expertise, I should note. But vehicle transport requires very high power density, so that you don't have a lot of choices that you can make in other applications, right? So there's a lot of applications like stationary battery storage that does not have such a high stringent requirement on the intensity, or like a power outputs and energy density, like a kilowatt hour per kilograms, for example. So for those applications, you might have other applications like compressed air storage, or like flow batteries that can do the trick. But for vehicle transport, for mobility applications, lithium ion is really the main workhorse, and I don't see it being replaced by anything else anytime soon. And now you can ask the question, well, all lithium ion is fine. What can we replace lithium ion cathodes and not use as much lithium, or not use as much as nickel or cobalt? And that gets to the thermodynamics of the materials. Our CEO, Kurt House, actually co-wrote a paper on this a year or two ago about the critical role of cobalt in lithium-ion batteries. The short note from that is that the cobalt is really, really good for lithium-ion battery cathodes. It increases the stability and also the performance, and that's the reason why all our smartphones, the lithium-ion batteries, are also are often made of pure cathode of cobalt oxide, right? They don't even bother putting nickel in there anymore, because in those applications, the performance is overweighing the price. Whereas in vehicle transport, that's not true, right? So you still have the different cathodes of NMC, NCA, and lithium iron phosphate LFP batteries, but that is not something that can be easily replaced. There's a fundamental thermodynamic reason for those things. So I think we're almost at time.
All right. Thank you so much, I-Kang, for your discussion and for taking up the questions. So I think we are, like you said, we're right on time, and I think we should jump on to the next